Good morning. Now consider another problem. A steel board is 10 meter long. At a temperature of 30 degree centigrade, what is the free expansion at 90 degree centigrade? Full stop. When the expansion is prevented fully, what is the stress induced, full stop, when the free expansion prevented only to 50%. What is the stress induced? Take alpha is equal to 12 into 10 power minus 6 per degree C, and Young's modulus of steel is equal to 205 GPa. So another interesting problem. A steel rod is 10 meter long at a temperature of 30 degrees centigrade. Let us write the given data. L is equal to 10 meter, that is equal to 10,000 millimeter at a temperature of T1 is equal to 30 degree centigrade. What is the free expansion at temperature of 90 degrees centigrade, when temperature rises to 90 degrees centigrade? Full stop. For this condition, again, when the expansion is prevented fully, what is the stress induced? When the free expansion is prevented only to 50%, what is the stress induced? By taking alpha is equal to 12 into 10 power minus 6 per degree centigrade, and Young's modulus of steel ES is equal to 205 GPa, that is equal to 205 into 10 power 3 Newton per millimeter square. Here it is asked to calculate free expansion delta LF is equal to question mark. Then asked to calculate temperature stress F is equal to question mark when delta is equal to 0, means when the free expansion is prevented fully. When free expansion is prevented fully means delta is equal to 0. And what is the stress induced when the free expansion prevented only to 50%? Again F is equal to question mark when delta is equal to 50% of delta LF. Free expansion prevented only 50% of delta LF, means delta L support is permitted to yield by only 50% of the free expansion. So this writing of this given values is very important, and what is required also to be known, that's also very important. So let us calculate free expansion first. Free expansion comma delta LF is equal to L into alpha into T. So we have L alpha T here you can write here T is equal to difference in temperature T2 minus T1, that is equal to 90 minus 30, that is equal to 60 degrees C, that is equal to 10,000 into 12 into 10 power minus 6 into 60, that gives us the free expansion 7.2 millimeters. Next, temperature stress when the free expansion is prevented fully. When free expansion is prevented fully, that is delta is equal to 0, we have temperature stress is F is equal to E into alpha into T. We have Young's modulus, it is 205 into 10 power 3 into 12 into 10 power minus 6, that multiplied by the temperature is 60, difference of 90 minus 30. So stress induced in this case it is 147.6 Newton per millimeter square. Next, when free expansion is prevented by 50%, then delta is equal to 50% of delta LF, that is delta is equal to 50 by 100 times of delta LF, means 7.2, that is equal to 3.6 millimeter. Therefore, temperature stress F is equal to E into alpha T minus delta divided by L. So knowing all the values, you can substitute here, that is equal to Young's modulus E is equal to 205 into 10 power 3 multiplied by 12 into 10 power minus 6, that multiplied by 60 minus delta is equal to 3.6, that divided by L is 10,000. So solving this, you will get 73.8 Newton per millimeter square. So when free expansion prevented by 50%, so we can see it is almost when there is expansion is prevented fully, then stress induced is 147, whereas when the expansion is prevented 50%, 73. So 50% of stress is induced in the bar. Consider another numerical problem. A steel bar 20 millimeter diameter and 6 meter long is connected to a pair of walls at a temperature of 120 degrees C. For this, it is asked to find the force exerted when the temperature falls to 40 degrees centigrade if number 1, the support do not yield, and number 2, the support yield by .1 millimeter by taking a Young's modulus of the material as 210 GPa and coefficient of thermal expansion alpha is equal to 12 into 10 power minus 6 degrees C. A steel bar 20 millimeter diameter, write the given data. Diameter of the bar is 20 millimeter and 6 meter long, length is equal to 6 meter, that is equal to 6000 millimeter, is connected to a pair of walls at a temperature of 120 degrees centigrade. T1 is equal to 120 degrees centigrade. For this, asked to find the force exerted when the temperature falls to 40 degree. T1, T2 is equal to 40 degrees C. This force exerted to be calculated under two heading. First one is force exerted P is equal to question mark when the support do not yield. When the support do not yield means here it is contraction. Free contraction is prevented fully, means delta is equal to 0. When delta is equal to 0, again force exerted P is equal to question mark when the support do not yield, the support yield by 1.1 millimeter. It is 1.1 millimeter. Given Young's modulus E is equal to 210 GPa, that is equal to 210 into 10 power 3 Newton per millimeter square, and thermal expansion alpha is equal to 12 into 10 power minus 6 per degree centigrade. So here force exerted is nothing but the P. If we calculate thermal stress, the force exerted can be easily calculated by knowing the cross sectional area of the bar. So let us calculate cross sectional area of the bar first. Cross sectional area of bar, it is area of steel AS, that is equal to pi d square divided by 4, that is equal to pi into 20 square divided by 4, that is equal to 314.15 millimeter square. Next, it is asked to calculate force exerted by the bar when the temperature of falls to 40 degrees centigrade. Here T is equal to T1 minus T2, that is equal to 120 minus 40, that is equal to 80 degrees centigrade. Next, first case, when the support do not yield, when the support do not yield, here delta is equal to 0. Expansion or contraction is prevented fully. We have thermal stress. So temperature stress can also be called as thermal stress, comma F is equal to E into alpha into T, that is equal to 210 into 10 power 3 into alpha, it is 12 into 10 power minus 6, that multiplied by 80 is equal to 201.6 Newton per millimeter square. So knowing the thermal stress induced in the bar, we can easily calculate force exerted by the bar. Therefore, force exerted by the bar, comma P is equal to stress induced, thermal stress induced into area of the steel, that is equal to stress induced is 201.6 into area 314.15. So it works out to be 63.33 kilonewton. Next, the support yield by, when the support yield by 1.1 millimeter, here delta is equal to 1.1 millimeter. Next, again thermal stress or temperature stress. Temperature stress comma F is equal to E into alpha T minus delta divided by L, that is equal to 210 into 10 power 6 or 10 power 3 into 12 into 10 power minus 6. Temperature calculated is 80 minus delta 1.1 divided by 6000. Solving this, you will get the thermal stress induced is 163.1 Newton per millimeter square, and force exerted P is equal to F into AS. Here stress is 163.1 into area of steel, it is 314.15. Solving this, you will get 51.23 kilonewton, that is equal to 51.23 into 10 power 3 Newton. So once we calculate stress, we can easily calculate the force exerted by the bar due to the prevention of contraction, and if the contraction is prevented by 1.1 millimeter. So consider another simple problem. An underground pipeline is laid in spring at 15 degrees centigrade, full stop. What stress could be induced on it when the temperature falls to minus 2 degrees centigrade in winter, and the pipeline is unable to contract full stop. Take coefficient of thermal expansion alpha is equal to 12 into 10 power minus 6 per degree centigrade, and Young's modulus E is equal to 205 GPa. Another simple interesting problem given. A pipeline is laid in spring season at 15 degrees centigrade, T1 is equal to 15 degrees centigrade. What stress could be induced on the pipeline when the temperature falls to minus 2 degrees centigrade in winter season, and the pipeline is unable to contract. The pipeline is unable to contract means the contraction is fully prevented, means delta is equal to 0. Taking alpha is equal to 12 into 10 power minus 6 per degree C, and E is equal to 205 GPa, that is equal to 205 into 10 power 3 Newton per millimeter square. It is asked to calculate the thermal stress induced in the pipeline. Here pipeline unable to contract means contraction prevented fully, that is delta is equal to 0. And one more thing you can see here is the pipeline was laid in the spring season when the temperature was 15 degrees centigrade, and in the winter season the temperature falls down to minus 2 degrees centigrade. Here T is equal to 15 minus of minus 2, difference of temperature, that is equal to 17 degrees centigrade. So when the expansion or contraction is fully prevented, we have the expression for thermal stress, we have temperature stress comma F is equal to E into alpha into T, that is equal to, given E is equal to 205 into 10 power 3 to alpha 12 into 10 power minus 6 and temperature 17 degree centigrade, that is equal to 41.82 Newton per millimeter square. So, a simple problem and it is an interesting problem. Let us consider another simple numerical problem. Steel rails of railway line each 12 meter long determine the minimum required gap between two adjacent rails so that they will remain stress free. Full stop. When there is a rise in temperature by 25 degrees centigrade, also determine the stress that develops in the rails if 60% of the expansion is prevented. Take Young's modulus of steel is equal to 205 GPa and coefficient of thermal expansion alpha is equal to 12 into 10 power minus 6 per degree centigrade. Another interesting problem, a steel rail of railway line each 12 meter long, steel rails of railway line each 12 meter long. For that it is asked to determine the minimum required gap between two adjacent rail. It is asked to determine the minimum gap between two adjacent rail. If another rail is placed here, what is the minimum gap required so that they will remain stress free. If you provide a minimum gap between the adjacent rail, these rails will remain stress free. when the temperature rises by 25 degrees centigrade, one another temperature is not given, only this itself is the temperature. Also asked to determine the stress that develops in the rails if 60% of the expansion is prevented. If 60% of the free expansion of this rail because of rising temperature is prevented, what is the stress induced by taking Young's modulus of the rail and thermal expansion of the rail as given below. Let us write first the given data. Given L is equal to 12 meter, length of the rail, that is equal to 12,000 millimeter. When the temperature rises, T is equal to 25 degree centigrade, and the Young's modulus is equal to 205 GPa, that is equal to 205 into 10 power 3 Newton per millimeter square. Alpha is equal to 12 into 10 power minus 6 per degree centigrade, and given that the amount by the which the rail yield delta L is equal to 60% of delta LF. Asked to calculate the gap, delta LF is equal to question mark and F is equal to question mark. The minimum required gap between the two adjacent rails is equal to free expansion. You might be seen when we go to railway station or when we are come across the railway lines, between two adjacent rails always there is a gap. That gap is usually provided for the free expansion or contraction. Even if it is contracted by an amount, so it will tolerate, no problem. But if it is expanded, if there is no gap, means because of no gap, if there is expansion, then rail will come up like this, leads to the toppling or this derailing of the train. To make this stress free, make rail stress free, always we provide a gap between two adjacent rail. That gap, the extent of gap is equal to the free expansion due to variation in temperature of that region. Here for the given value, the minimum gap between adjacent rails is nothing but free expansion. That is delta LF. We have delta LF is equal to L into alpha into T. Given length of the rails, temperature we know, and the coefficient of thermal expansion we have, we can easily calculate the minimum gap. That is equal to 12,000 into 12 into 10 power minus 6, that multiplied by 25 degree centigrade, that is equal to 3.6 millimeter. Next, if 60% of free expansion is prevented, that is delta is equal to 60% of free expansion is nothing but 3.6, free expansion is equal to 3.6, that is equal to 2.16 millimeter. The stress induced, we have temperature stress comma F is equal to E into alpha T minus delta divided by L, that is equal to Substitute the values 205 into 10 power 3 into alpha 12 into 10 power minus 6, to temperature it is 25 degree minus delta is 2.16, that divided by 12,000. Solving this we will get the stress induced is 24.6 Newton per millimeter square. So in this way you can solve any problem by understanding the concept of the temperature stress for various conditions. So with this we will conclude this part of the thermal stress, and in the next class we will meet for temperature stress in compound bars.